NASA's daily update on 3i Atlas just came out, and honestly, the one line everyone was secretly hoping to see still does not exist. There's no behavior settling into a stable state with no activity final pattern. Instead, buried in all that specialized language is a pretty clear reality. 3i Atlas is not stabilized. If you've been keeping up with this object with me, and you don't want to miss what happens if it keeps refusing to calm down, stay with me till the end, because today's numbers might be the clearest sign yet that this interstellar comet is still in the middle of its story, not the epilogue. Before we continue, if this has your attention, you can subscribe, turn on notifications, and hit like anytime. And for the best viewing, switch to full screen and enjoy what's coming next. The day started like any other check-in. New images came in, fresh brightness measurements, position data from ground-based telescopes, and a couple of spacecraft cameras. Nothing about the plan implied that anything significant was coming. This was supposed to be just another point on a smooth curve view? No. Another routine data point that would confirm what we thought we already knew. On paper, that curve is simple enough. After perihelion, which is the closest point to the sun, activity should drop off. Less heat means less gas and less dust. The light curve slides down. The jets weaken. The comet's motion starts to look more and more like a quiet object just coasting along its orbit, minding its own business. It's what happens to pretty much every comet we've ever watched. They flare up near the sun, and then they relax. Simple physics. When they laid today's brightness points onto that curve, it broke, and I mean really broke. Instead of adhering to the anticipated decline, the real data sits high. It is fainter than it was at peak, sure, but it's still brighter than it should be at this distance, way brighter. The line that's supposed to bend downward just flattens out, as if someone had taken the curve and refused to let it fall. That's your first hint that things aren't stabilizing the way they should. That's your first warning sign that something else is going on here. If this were just leftover dust hanging around from earlier activity, the inner coma would appear sort of blurry, soft, washed out, and indistinct, like fog slowly dispersing. But when they stack today's deep exposures, that's not what appeared on the screen at all. The inner coma still has a sharp core with a fresh, faint arc wrapped around it, a new shell of material that wasn't in the stacks a few days ago. Think of it as a time stamp in dust. It's near the edge of a new pulse that's still close enough to the nucleus that we can see its shape before it gets lost in the background and lost in the noise. This is fresh activity, aerosol activity, not old material slowly drifting away. Farther out, the tail still has a defined spine. There's a bright, narrow lane running down its middle, supplied by a concentrated flow that's clearly still active. It's not diffuse, it's not spreading out the way you'd expect from dying jets. On one side, today's images show a slight thickening, like a side fan of material has strengthened again, like something turned back on. That's not the geometry of a system shutting down. This is a geometry that's being updated in real time. That's a comet that's still doing things. Then, the rotation check comes in, and this is where things get really interesting. To see how 3i Atlas is rotating, NASA's teams observe how its brightness fluctuates over the course of hours. Different regions of the comet's surface come into view. Some areas are more active than others. Some reflect more sunlight, so the brightness goes up and down in a pattern that repeats with each rotation. For a stabilized comet, the light curve repeats cleanly. Peaks arrive on schedule. The curve shape remains the same, rotation after rotation. It's predictable, boring, even you can set your watch by it. Today, when they folded the newest photometry over last week's best fit rotation period, the peaks drifted. They didn't line up the way they were supposed to. Something had changed. The main maximum shows up a little earlier each cycle than the old period forecasts. And there's a secondary bump that used to be small and fuzzy. It's grown sharper and more consistent. Every time it appears at the same phase now, it's almost as strong as the primary peak. Like a second heartbeat that made the sudden decision to announce itself, like a second active region that wasn't contributing much before. But now is a major player. To make everything line up again, they had to shorten the period slightly. That means the comet has spun up again, just a bit. The rotation is faster than it was last week, and that stronger second peak tells you something important. A second active region has become a regular, reliable contributor to what we're seeing. It's not random anymore. It's not occasional. It's locked in. It's part of the pattern now. So the spin isn't stabilizing either. It's still being nudged by forces we can measure but can't fully predict yet. Forces that are changing the fundamental dynamics of how this object moves through space. Now we get to the part that decides whether this is just interesting or genuinely unsettling. The orbit solution. Every new batch of positions gets pushed through the orbit solver. It's sophisticated software that takes all the observations and figures out exactly where the comet is and where it's going. Gravity does most of the work, right? The sun's pull, the planet's tiny tugs, all of that is straightforward physics. We've been doing this for centuries. We're really good at it. The complication is the force other than gravitational. The tiny rocket pushed by blasting gas and dust jets off the nucleus. When material vents from the surface, it doesn't just drift away, pushes back on the comet itself. It's Newton's third law, action and reaction. It's small, but it's real. And it adds up over time, over weeks and months. It can shift the orbit in measurable ways. If 3I Atlas were stabilizing, those jets would be fading. Likewise, an additional acceleration term would slowly drop toward zero. The pressure would get weaker and weaker. In the ideal quiet case where the comet went dormant and stopped venting, you wouldn't need it at all. The orbit would be pure, Newtonian, gravity, clean, and simple. Today's solution still needs it, and it needs it badly. Worse, it needs it in a slightly different direction than yesterday. That is the key point. Using yesterday's parameters, the predicted positions and today's actual detections don't match. The residuals aren't random scatter, which you'd expect from measurement noise. They lean systematically to one side, which means the model is wrong in a specific, measurable way. The push has changed direction. To fix that, the fit has to tilt the thrust vector again and keep its magnitude at a level that simply is incompatible with a calming object. The comet is still pushing itself around in ways that constantly shift. From day to day, both the direction and the force of that push are evolving. So you have three independent signals painting the same picture, three completely different types of measurements that all tell the same story. Brightness that refuses to follow the expected fade-out, inner structure that shows a new shell and a persistent spine in the tail. An orbit that still requires a changing self-push to explain where the comet actually is in space. And sitting over all of that is a rotation period that's still drifting, as well as a second active region that has become a permanent part of the heartbeat. That's what not stabilized. Looks like in real data, that's what the numbers are telling us right now. It's not one weird measurement. It's not one anomalous data point that might be an error. It's a consistent pattern across multiple independent lines of evidence. In fact, it makes uncomfortable sense when you think about it. The pass near the sun didn't just scorch the surface and leave it kicked off a slow, deep thermal process that's still working its way through the interior. Heat doesn't move instantly through ice and rock. It takes time, days, weeks, maybe months. The outermost material responded first. Obviously soft ESOS, shallow fractures, and loose dust. Those gave us the early wild jets and bizarre coma shapes that caught everyone's attention during the time that this comet was approaching perihelion. But 3I Atlas isn't a clean, uniform ball of ice. It's not a flawless snowball. It's a layered body with cracks that formed around another star, probably in conditions very different from the solar system we live in, and then spent billions of years in interstellar space. Got countless years of cosmic ray bombardment. Billions of years of micrometeorite impacts. Billions of years of thermal cycling as it passed through different regions of space with different radiation environments. Inside, there are pockets of volatile ice buried along ancient fracture planes, each at a different depth, each with its own minimum temperature, each one waiting as the heat wave spreads further inward, spreading through the interior like a slow wave. One pocket after another crosses its critical temperature, and when it does, chemistry takes over. Physics takes over. When that occurs, the region does not care that the comet is outbound and moving away from the sun. It makes no difference that we're past perihelion. Temperature wins. The pressure grows, and the ice sublimates. Gas expands. It vents. Every time one of those deeper pockets turns on, three things happen at once, and they all matter. They all contribute to what we're seeing. First, brand new gas and dust enter the coma. They replenish what's already there. They keep the brightness higher than the models expect and carve new shells into the glow we can photograph. That's why the brightness isn't dropping the way it should. That's why we keep seeing fresh structure in the inner coma. Second, jets from new locations add torque to the nucleus. They're not coming from the same places the old jets were. They're coming from deeper layers, different parts of the surface, maybe regions that were dormant before. They twist the spin just enough that the rotation period and brightness pattern change again. That's why the peaks in the light curve keep drifting. That's why we have to keep updating the rotation period. Third, the direction and strength of the outgassing force shift. The total push on the comet changes, its magnitude changes, its direction changes, and that forces NASA to modify the non-gravitational term in the orbit's solution to match reality. To match the actual location of the comet against where pure gravity says it should be. From the outside, looking at our data, it looks like an object that refuses to stop rocking and flatten its light curve in a spin. refuses to settle into a streamlined tail structure. It resembles an object that's fighting the models from the inside. If we could somehow see through all that ice and rock, if we could peel back the layers and look at what's really happening, it's a nucleus trying to not quite reach a new balance under enormous stress. It's an object that got hit with more heat than it has seen in billions of years. And it's still figuring out how to respond. Still adjusting, still venting, still changing. That's the real meaning of today's not stabilized update. That's what they're actually telling us. When you strip away the technical jargon and the careful language, it doesn't mean fragmentation has started. Let me be clear about that. There's no confirmed second core splitting away. No clean row of debris trailing behind like breadcrumbs. No devastating brightness surge that screams breakup in progress. No obvious signs that the nucleus has cracked apart into major components. We are not seeing that. But it also doesn't mean we can treat this as a quiet outbound comet anymore. We're past that point. We can't just assume it's going to follow the normal pattern and fade away peacefully. The data won't let us make that assumption anymore. A stabilized comet gives you predictable behavior. It gives you a rotation period that holds steady, cycle after cycle, activity that scales predictably with distance from the sun. Following a simple mathematical relationship we've verified on dozens of other comets. A non-gravitational push that shrinks smoothly as the jets die down and eventually becomes negligible. Eventually shrinks to the point where you ignore it when calculating the orbit. 3. I-Atlas is giving us something else entirely. A rotation period that remains creeping, changing, just enough each week that you have to keep updating your models. You can't use last week's value, you have to recalculate. Activity that stays high and pulses in waves that don't match the simple distance relationship. The brightness that refuses to follow the inverse square law the way it should. A cell that is still required, still changing direction, and still linked to visible structures in the coma that we can photograph and measure. This isn't theoretical. This isn't speculation. This is what the measurements show. This is what multiple independent observatories are reporting. This is real. From here, there are really only two paths forward, and we don't determine which one this comet will take. We're at a fork in the road, and the data hasn't told us which way we're turning yet. On one path, the deeper layers finish venting over the next few weeks or months. The heat wave works its way all the way through. The last pockets of volatile material exhaust themselves. The spin-ope slows down and eventually fades away. The rotation period locks in at some final value and stays there. The jets weaken as the last reserves of gas run out. All of these curves finally start to slide in the way we expect, based on decades of watching other comets. Not stabilized, become stabilizing, and eventually just fading. The brightness drops, the tail goes away, the structures blur out. The comet becomes a quiet chunk of ice and rock, returning to interstellar space. Its story, basically over. It had its time. It flared. It was interesting for a while, and now it's done. On the other path, the pattern continues. More late bursts of activity, more unexpected brightenings, more force applied to the nucleus that keeps modifying the spin, putting more strain on a body that's already been stretched, cracked, heated, and twisted within an inch of its structural life. More pressure building in pockets that might not be able to contain it anymore. At some point on that second path, and we don't know exactly when, or how, the internal structure loses its capacity to absorb new changes. There's a limit to how much stress ice and rock can take. The fractures that have been opening and closing start staying open. The cracks propagate. The pockets of pressure can't be contained anymore. The underlying integrity fails. The spin becomes unstable. The nucleus can't hold together anymore. That's the time not stabilized. Stops being just a line in a daily update and transforms into the background for something far more dramatic. Something we'll be talking about for years. Something that might make this one of the most important interstellar objects we have ever seen. Right now, today, we don't know which way this goes. What today's daily check tells us very clearly, and without much room for interpretation, is that we are not at the quiet end of the story yet. We're still in the midst of everything that's going on. We haven't reached the resolution. We haven't seen the final act. The heat is still working its way through the interior. The pockets are still venting. The spin is still changing. The orbit solution still needs that changing push term. The brightness is still higher than it should be. The coma structures are still new and active. Every one of those facts points to something that is still evolving, still responding, still under stress. This comet came from a different star system. It was born somewhere else. It formed in the debris disk around a star we don't even know the name of, a star we probably can't even see from Earth. It survived billions of years in the cold of interstellar space, drifting through the void at incredible speed. It somehow ended up on a trajectory that brought it into our solar system. It swung closer to the sun than Venus's orbit, experiencing temperatures and radiation it hadn't felt in billions of years. And now, moving back outward, it's refusing to quiet down on schedule. It's refusing to behave. Every day that passes without stabilization is another day closer to finding out what happens when a stressed interstellar visitor decides it's had enough. Another day closer to finding out what this object is really made of, what it can really endure, and what occurs when you push something from another star system to its limits. The teams watching this comet are checking every day. Times a day actually. New images, new measurements, new position data. They're watching the brightness. They're watching the rotation. They're watching the orbit. They're watching the structure within the tail and coma. They're looking for any sign that tells them which path we're on. So if you want to see whether tomorrow's update finally shows those curves bending towards stability, whether the brightness starts dropping the way it should, whether the rotation locks in and the jets finally fade, or whether 3i Atlas decides to rewrite the script again and show us something we've never previously observed from an interstellar object, make sure you're subscribed and stay tuned, because this story isn't over, not even close. We're watching something that has not yet subsided, something that's still changing, something that might still surprise us. And in astronomy, when something surprises you, that's usually when you learn the most. The textbooks get rewritten at that point. As always, stay curious, and I'll see you in the next one.